So our, I guess, final presentation before my own closing remarks is from Dr. Guang-Hong Chen. He's the Charles A. Mastretta Professor of Medical Physics and Radiology at the UW-Madison. Chuck was my advisor, so I have a warm place in my heart for him, and so that is wonderful. He is a pioneer in the development of X-ray and CT imaging systems and novel reconstruction algorithms. He has over 250 scientific publications and is an inventor on more than 40 US patents. Dr. Chen has mentored over 30 PhD students and significantly contributed to medical physics education, developing courses and textbooks on radiation physics and dosimetry and data science in medical physics. He's a recipient of the Kellett Mid-Career and the Wharf Named Professorship Awards. He also holds fellowships in the AAPM, AIMBE, and SPIE. He's a distinguished investigator with the Academy for Radiology and Biomedical Imaging Research and has assumed leadership roles in professional societies, including the AAPM, the SPIE, ISCT, and RSNA. Guang-Hong.
Thank you so much, Cynthia. That is an absolute pleasure to be here and to share something with you today. So before I start, I would like to thank all my colleagues, friends, former students who contributed to this talk tremendously. If there is any credit should go to them. If any mistakes are mine. So I was asked to talk about artificial intelligence in CT imaging, but I was thinking it could be a big mistake if we talk about artificial intelligence without really understand and appreciate the marvel of human intelligence and its success in CT image reconstruction. So that said, I will start with this celebration again and start with the Nobel citation for Dr. Alan Cormack and Sir Godfrey Hansfield. And for Alan, what the citation is, he was the first from a theoretical point of view to analyze the conditions for demonstrating a correct radiography cross-section in a biological system. He published his analysis of the problem in 2 scientific publications. I'm glad Norbert also used this exact same 2 publications. And Dr. Cormack is a physicist, and his style is a genuine physicist manner to do research. That means he derived elegant formula for reconstruction and conducted really simple yet effective experimental study to consolidate, to validate his studies. And this phantom study that Norbert showed this morning, and I add on that what I like most is he really do the to show the image can be correctly reconstructed with all the profile, experimental data and theoretical data match really well. That is a way to do that. And, his major development is the image reconstruction formula. Later, I will make a comment about that. About Hansfield, and the citation is this: he has made really decisive contribution for introducing CT in medicine by constructing the first CT system and used in practice as the movie and film, and many of us touched upon that. That is really a wonderful thing. And yet the image reconstruction, since Sir Godfrey Hansfield is an engineer, so he really does not go to really complicated fancy mathematics. It's really just use the basic algebraic approach. That is the standard way in engineering sciences, just do the least square feet to do reconstruct. You have 4 unknowns, you have 4 equations. Of course, all of us, I think we can solve this problem. That is how his image was reconstructed by 80 image pixels and the algebraic reconstructed. And these days, of course, when we talk about CT and image reconstruction, it's all about filtered back projection. That filtered back projection was not developed by either Hansfield nor the Alan Cormack. No, it is actually traced back to Johann and back to 1917. That is even 60 years before the CT was developed. And that is the original paper. I don't know a single word Thomas Pro can interpret for us, except the mathematical formula looks like I can understand that. Okay, and lucky enough, is back to 1986, and J.C. Park actually translated this paper in English and published IEEE such that we all can understand about that, all right? But all here, I want to really, make a foul here, okay? Because this is really CT and clinical. I'm not supposed to talk about any formula, but I really want to bring you to the formula, the bottom formula 3 prime. That is amazing. You say, why it is amazing? Because it all says epsilon goes to 0, but epsilon goes to 0. The first term goes to the positive infinity, yet the second term goes to negative infinity. So what the heck is going on here? So, but here really the truth is truly remarkable and make me so, admire this work so much is it tells us a very simple truth called infinity minus infinity equal to a finite number. And that is the beauty of the human intelligence, actually. And how does that work, actually? If you think that is the lecture notes written 20 years ago, perhaps I saw those before, and when he was graduate student, there is really about the RAM filter. The right hand, everybody talk about the RAM filter, that is the home, right? It is in the Fourier space, but really when you translate those things back into the spatial domain, it is about 1 over distance square filter. And that is the problem because it's minus. So it is just when rho goes to 0, just immediately send everything down to the hell. That is how I joke. But that is the problem. Is that if you use that to reconstruct image, that is absolutely wrong. Okay. The beauty actually is when you really translate this one, from spatial domain, transform to the Fourier domain, and then you push this rho equal to 0 infinity. And for the Fourier space, it's just k into large k. And as soon as you go to large Fourier space, and you figure out actually do the math correctly, it is beautiful because it tells us we should not send everything to the hell. Okay, that is negative infinity. We need something to raise it up to heaven. And that is at rho equal to 0, you should put an infinite positive number. And that is positive number and negative number exactly cancelled to generate the image all of us enjoyed in the past 50 years. And you say, really? Okay, that is the filter I show you, and I give you really amazing in the modern, digitization. How do we implement that? It's 3 statements. It's really scary, and that done. Set all the values at even index n to 0. Why? Because it is all negative. Why we send something 0? It does not make sense. Number 2 is multiply by its value at odd index by a factor of 2. You send the even to 0, odd multiplied by 2, and then transfer negative infinity to positive infinity at n equal to 0, and put together. That is the filter on the right-hand side. You say really at n equal to 0, just send, because the 1 over delta x squared, when delta x pushes down to 0, of course, that sent to the positive infinity. And that is beautiful. And here I show you why we acquire data and use this digitized filter, RAM filter to filter it. And it is beautiful because outside of image object, you have negative wings. And inside image object, all signal becomes positive. And now you back project. That means you send signal back to image, and the positive side, that is yellow, and the negative wing just generate negative numbers. For instance, from one view angle, you change a different view angle. You see the negative things and positive things outside the image object start to cancel each other, and you just keep going. Go through all 360 degrees, and perfectly sharp image is reconstructed. That is the yellow gold. That part is the image object. Outside is 0, right? Because that is the pinkish. That is the beauty and awe of the human intelligence. Okay, how in the reconstructions. Then we will talk about, AI later, and we'll really, I want to start with here to tell you what is AI reconstruction in modern language. It is beautiful, actually. That image I just showed you, the filtered back project, is nothing but deep learning. You say, how can that be? Let me unpack this message. For you have data, right? You acquire data and have sinogram, and you start to do the filter. Filter is what? Convolutional layer. You just, one layer, you just convolve, you generate the data convolution. And then back project is a set layer, essentially just do a sparse connection. Back project, that is the 3-layer neural network, and 3 layers being considered as the deep neural network. 2 is not deep, but 3 is deep. That is precisely deep neural network, and FBP is that. And particularly, it's human intelligence here is going. There is no training data needed. All the parameters being fixed by human brain. Okay, so there's the absolutely generalizable. You don't need to worry about anything because FBP is, generalized to anywhere we want to. Works pretty well, except for the extremely low photon counts. Of course, we have streaks, and you have highly attenuating metal object. Of course, that is just photon stop. That does not work well. So to handle this photon starvation, so you need to think, that thing, everything is deterministic. We need to introduce statistics. That is how the MBIR or model-based iterative reconstruction, all these things comes in. But that is not new either, because that is standard statistical learning process. All have been doing back to 20 years ago to do model iterative reconstruction. You do a handcrafted prior model. What kind of image you want, you just write down a prior and send that prior into the reconstruction. So let's maximize this likelihood, and then you generate an image. That works pretty well, and all the vendors, commercialized this in this one way or another. It works pretty well. Noise get well controlled, noise streaks get well controlled. That is all good things. But we also, this morning, Dr. Li-Feng Yu and many of us, we reviewed that, and we see that the major challenge is due to nonlinearity of the reconstruction. The image reconstruct image quality is not uniform. Somewhere really nice, somewhere is really poor. And how in clinical practice, how do we use this image? And for medical physics side, how do we do the quality assurance? That is a big challenge. And the noise power spectrum gets shifted, and that is the spatial resolution, and all those things change with image contrast. So even the iodine really sharp, you have soft tissue lesion, and the boundary just get blurred, and actually introduce a lot of false diagnosis. Okay, so the radiation dose reduction did not go as one initially expected, as Dr. Li-Feng Yu summarized this morning. Okay, so now we can grasp a little bit artificial intelligence. Why? Because artificial intelligence is nothing, just deep neural network plus what? Statistics. Now we have deep neural network, that is the FBP, statistics as MBIR. Let's just put everything together and to do the image. That means all the dark kind correction, gain correction, all those things in the back engineering domain. And let's just wipe everything off by a deep neural network and let you sit back, relax, and let neural network to do things for us. But this time we need to do what? We need to feed this neural network some data to let the neural network to learn what to do. Okay, there are many different ways to that, and that is how, I motivated by FBP, motivated by MBIR. So that first thing I want to say, ask my students and work together with me and say, okay, let's challenge deep AI a little bit to see whether AI can do what our human intelligence did. That is negative win, positive thing, cancel each other to reconstruct. Can we figure that out, that filter? That is initially what I wanted to do. And we'll put together a deep neural network and have 3 modules. One is data correction, that is better detector, the pixel and the gain correction, all those things in the sinogram domain, we can do that. And data filtration model, that is just to simulate essentially the human intelligence to do the figure out that random filter thing. Okay, and the data domain transform, that is do the backprojection. We put together, and as you can expect, the FBP is deep neural network, statistical reconstruct is statistics. So put together, of course, it should work, right? So that is we train this whole thing, and then we call it the intelligent ICT-NET. And you can do, actually, it's quite nice. You can do the dense view, that is standard clinical reconstruction. MBIR, that is the iterative reconstruction, ICT-NET. Image reconstructed relative reference is quite good, all right? And the area, and you can do, the nice thing is this time you actually can go a little bit more relaxed condition. In clinical condition, about 1,000 view angles, and use this trend as ICT-NET. You just give like 200 view angles, it still reconstruct image quite well. So that is something better than the original FBP in my eyes, okay? So that is one thing. Second thing is it automatically controls the noise because statistics has been built in the whole process. That is 108 MAS FBP reconstruction on the left and 12 MAS the middle, and the same 12 MAS reconstructed by ICT-NET. You can see really the image reconstructed really well. Because noise get knocked out as the central part, you can see the little ring artifacts start to appear because with the original 108 MAS and some, because noise covered the ring artifacts, you don't see that. That means when they have to do a little bit better to calibrate the detector non-uniformity response. All right, and you can highlight the lesion and you can see lesion really well. And you can check the point spread function, like that means spatial resolution, and that it uniformly is across all the different dose level, and the spatial resolution preserved very well. And also check noise power spectrum and nice donut shape noise power spectrum, just like standard FBP. Why? Because we trained the model using the standard FBP. Of course, it should behave like FBP. There's nothing really surprise. And they go to the major thing we want to challenge is generalizability. We trained all these things in the chest CT, and we want to try to apply to, for example, abdominal CT to see reconstruction quality change. Actually, it does not. If you have sparse field, dense field does not change. It go to pervasive, it does not change quality. And even we can challenge more because we trained the neural network using the 100 kV data. That is the chest standard protocol. And we want to say the same training neural network can reconstruct image if we acquire data, for example, head, that is 80 kV, or what do the 120, 140, whatever, you know, the tube potential level, and do reconstructing the exactly same training neural network, and it does perform really well, and it keeps the reconstructed image quality the same thing, basically. Okay, and the final thing I want to really encourage, like young a student postdoc when do this is really whenever you do, just do the quality basic sanity check. It noise in, noise out. You don't want to send a noise in, no data sending generate human anatomy. That is scary, right? So we also check that then input sinogram that is noise and send to the FBP reconstruction that and noise, and send the same noise sinogram sent to the ICT-NET. You get a noise and you can check the noise power spectrum, both generalized, nice donut shape noise power spectrum. That basically has the sanity check. That is the thing. Okay, so with that success, and one of the former employee from Mayo Clinic joined me, Juan Montoya, in back to 2017, 2017 that year, and he wants to do something. I said, okay, let me challenge you something better. I only give you 2 views because that is standard CT scan have 2 scout views. Why not we reconstruct whole CT image volume using 2 scout view angles? So he asked, why do you do that? I said, well, wait for a moment. For the auto exposure control, for example, you need to really build the tomographic human model to really tell you, how to prescribe those. I think he tried really hard and turned out everything worked nicely. That is use a lot of data to train, and MDCT, that is the patient, and with 2 scout view angles, you reconstruct images. Pretty nice from all the view angles. You can see it reconstruct really well. But let me give you one. I never say this 2 view reconstruct images using for diagnosis. No, I said this for the auto exposure control and for other technical purposes. All right, and generalizability, we trained using the chest CT. We apply to the 2-year-old, 6-year-old, even the phantom, the Tokyo phantom. And no matter what you try, as long as you have a human-like anatomy, it works well. Even for a pig, it works pretty well. But I forgot to put my backpack in. And when I put backpack in the scanner to get 2 scout view angles, as that is scary because that is totally out of distribution. Backpack is not human anatomy, so it will generate human anatomy-like image for backpack. That is wrong, okay? Yeah, so good. So that is basically what I said is really the synergy between the human intelligence and artificial intelligence. We more put them together, actually can do something amazing to solve some challenging problem. Can we do something even better? Even better, just as what I said, human intelligence in just synergy to integrate these 2 things to do something more challenging, like interior tomography. Leifeng talked about interior tomography and not come to the practice yet. And this I want to use this slide. Actually, recently, one of my students just made absolutely one of the most amazing progress in the past 50 years. Here's what I tell you. So that is when lunchtime we'll talk about things here. Nobody talk about we need to mention Harry Peters. And back to 1971, the year I was born, and 1971, he published in his PhD thesis, what Perry did said is, when you have the parallel beam, acquisition with all the straight lines acquired, he said, you simply just back project those things into the image space. You generate a blurred image, just like this one, blurred image. So that blurred image is nothing, but the blurring panel is 1 / distance. That is well known for parallel beam. That is well known. And after 8 years, actually, Guang-Hong published a paper. He generalized that result to the divergent fan beam case, but it only works for the 360-degree full scale. Okay, 360. And why it works that way is essentially. Did I push? I missed that. Can I go back? I have that image picture I want to show you. So it is really, truly marvelous. Since, okay, this image is really the cool thing is you have any point like x0. The thing is you have 2 source points. That's 360 degrees. You have always 2 source points. And the distance L from the L0 to first source and second source added together, that is the chord, length of chord. And that length is nothing but related to the radius of this scanning trajectory in perfect way with the projection view angle. So everything get nicely canceled out. That is why Guang-Hong was successful back to 1978 to generalize that. But if you generalize to short scan or super short scan case, nobody knows how to do that. And my student, Chen Zhugang, did in 1 year ago is, he amazingly said, don't do the direct back projection like Terry Peters. Don't do that like Guang-Hong. Let's multiply by the measured projection data by a weighting factor. That is strange magical weighting factor. It's like put together and you do the back projection. And we can prove that mathematical proof. If you do that, the back projected image is nothing but the true image convolved with 1 / distance. And that is universally correct for any image pixel. And that means you don't have to have large detector. You can always use truncate detector to measure data because back projection is local operation. So that is really amazing. But that is not the image. Image is you get a back projection image. That is the true image convolved with a 1 / distance. But that's easy now because that is universal. It's okay, let's just train a deep neural network to perform what? Perform this deconvolution, to deconvolve this 1 / distance, and it can get image reconstructed. That is the work, he did, and just do this work and perform deconvolution. And that is universal, just train one single neural network, train and work for any ROI you want to reconstruct. Reconstruction is almost perfect, okay? And generalizable to anything, to even numerical simulation data, whatever for photon counting CT, whatever we tried. It's just single reconstruction network. It works for all the cases. Why? Because human intelligence has already helped figure out whatever you do the back projection is nothing but the true image convolved with the 1 / R. If you learn how to deconvolve with 1 / R, that has nothing to do with the image content, of course. It should universally work for all the cases. So that is really the beautiful thing. Okay, since in the end, and since some young folks are here and say, what is the future of artificial intelligence? Let me bring you one thing, okay, in 3 minutes, if you allow. Okay, that is inspired by the non-equilibrium statistical mechanics. And that is thought actually from Einstein back in his magical year, 1905. All 3 things, he's famous, all 3 things are published in 1905. And that is the Brownian motion. So it is a pollen particle suspended in the liquid. And that pollen particle, what is the motion of the pollen particle? And what Einstein discovered is that motion is controlled by this diffusion equation. And that diffusion equation is from whatever original one and convolved with a Gaussian, rolling Gaussian filter. And they say why that things has anything to do with deep learning. And that I tell you, in the past 3 years, the most impressive progress in machine learning and AI is this thing, okay? So essentially, the basic idea is you start with, now we are celebrating CT50, right? We have the firework, okay? That attributes Dr. Radon. Okay, what he said is CT50, that is really highly structured thing. It is really difficult to sample, to understand. But what Einstein did is in the pollen particle is let's just do a diffusion. That means you inject noise into the whole process. So eventually, whatever distribution you have, your data, in the end, just become what? Become a uniformly Gaussian distribution. And Gaussian distribution, that is something computer can handle easily. So, but it's a why? Why do we need that? But the beauty is do the reverse process. Okay, now you're from really the Gaussian noise injected things, go back to do the reversion, to reverse thing. And reverse thing, you can go back from noise and condition on the original image. You can go back to really to trace back to the original distribution. What is that? That basically means you have a noisy image. Now you go back to do what? To do the denoising. You have artifacts contaminated things. You go back to do what? You de-streaks, you do the artifacts. All reconstruction works just been done. And that is, you can show that, and from left to right is from Gaussian noise, and you can quickly just go back to reconstruct actually the nicely ordered thing. But the beautiful thing is, okay, from the thermodynamics tells you the entropy always increase. That means from the order, you always go to disorder. And how can you go back? Go back, you always need the driving force, external force. And that external force, that is the second term is the delta X. That is the gradient of the distribution. And that is nothing but just the force in the potential well. Now that is how it works. And we use this whole thing and work, rundown use that to do the denoising to generate really the low dose CT image that is using the quarter dose CT, and you do the diffusion model, you really remove the noise and compare with the routine dose. It works pretty nicely. And you can also do from single kV CT scan, contrast enhanced single kV scan. Using the same physics principle, you can go back to try to figure out what is the corresponding iodine map. After training, actually can do that, and you can perform the beautiful thing. You may ask, why do you need to do that? I want to respond to Dr. Williamson just talked about. It's confidence. You do the AI, you need to have confidence interval to say whatever the results, what is the error? What is the error bound? That is using this new technique can provide us uncertainty map. So whatever AI prediction, it can tell you what is uncertainty. For example, this one, the middle part, that is the iodine and the artifact. That is the part AI cannot predict well. That tells you this region don't trust because that's something goes wrong. Other low, the uncertainty level, that means AI is pretty certain that is the right results. At least I think the first step, the entire AI community should do in medical healthcare domain is really everything we need to quantify the error map. Without that, we cannot really give our clinicians any confidence about how to use that. And the VNC image can do the same thing. Again, the beautiful thing is uncertainty map. I give you this, Eric, I give you this uncertainty map. You can compare with the image. You say, okay, this region I don't trust. They said it's not trustworthy. And wherever trustworthy, we use it, okay? So that is the new directions and physics, non-equilibrium, statistical mechanics inspired deep learning. And that is the major theme in the past 3 years in AI community. That said, let me try to summarize, and 3 points I try to make is using AI actually can revitalizing the CT image reconstruction, basically unveiling hidden patient similarities to deep neural network. That is how we don't use handcraft fry any longer. We use the patient data to really learn the regularizer. Second thing is we need to foster synergy, human AI calibration as a key to tackling complex challenges in CT image. Final thing, what I said is really we need to have physics informed AI model, not just purely data mining. Okay, so finally, all AI model is just model. How do we trust that? Let's remember what George Box used to tell us. All models are wrong. The right question actually is the practical question is how wrong they have to be to not be useful. So if we're keeping that in mind, we can use AI, but we can really understand how to approach, how to ask the right questions, how to use them correctly. That said, thank you so much for your attention.